Good afternoon, folks. Thank you for all of you who responded to that. We've been working on this all up. It's my great pleasure to introduce today's Colloquium speaker, who is our own Rahul Nandkishore. Rahul earned his bachelor's and master's degrees from Cambridge University, Trinity College in 2008. Completed his PhD at MIT in 2012, working with Leonid Levitov. After a postdoc at the Princeton Center for Theoretical Science, he joined the CU Physics Department as an assistant professor in 2015. Since he joined our faculty, Rahul has published high-profile work on a whole range of topics under the broad umbrella of theoretical condensed matter physics, including long-range quantum interactions, quantum order, chiral superconductivity, fractons, and many others. Rahul has supervised a series of PhD students and postdocs, and his group members have consistently gone on to prestigious positions after finishing at CU. He's been a fellow at the Center for the Theory of Quantum Matter, CTQM, since he came to CU, and last year he took over as CTQM director. Today he'll be speaking on the topic of ergodicity breaking in quantum dynamics. So please join me in welcoming Rahul Nandkishore.
Thanks, Tobin. Great to be here and see so many of my colleagues and students, and to share with you, sort of strand of research that I've been pursuing over the past decade, which I'll put under the sort of title of ergodicity breaking in quantum dynamics. So this is work that's been done and developed over many years. A lot of people deserve thanks, but 5 in particular. So this is Vedika Khemani from Stanford, Andy Lucas, our colleague, local postdocs David Stephen and Oliver Hart, and my just graduated student Charlie Stahl, as well as many other people who are listed below alphabetically. So with that said, let's get on to the talk. I sit on the condensed matter floor in Gamow Tower, and the governing slogan of condensed matter physics is the idea that more is different. So when you take many interacting degrees of freedom and put them all together, you can get new sorts of emergent phenomena. And historically, the condensed matter has mostly focused on systems in thermal equilibrium, where, and sort of in that setting, the possibilities by now are relatively well understood. In contrast, I would say non-equilibrium systems are really terra incognita, and they can support new phases and new phenomena with no equilibrium analog. And certainly I view understanding non-equilibrium many-body physics as the great open problem for condensed matter theory in the 21st century. And that's what I'm going to be telling you about today. And as it turns out, that understanding non-equilibrium many-body quantum phenomena is going to require revisiting essentially everything that we thought we knew about statistical mechanics. OK, so the way this talk will proceed is as follows. I'll begin by introducing the notions of quantum thermalization and ergodicity. Then I'll talk about how we can break ergodicity, and I'll show you 3 routes to ergodicity breaking. This is ordered chronologically in terms of when they were discovered, but you can also think of this as being in sort of increasing order of robustness in a sense that will hopefully become clear as the talk proceeds. And then finally, I will conclude. OK, so let's start by setting the scene. So when you open up textbooks on quantum stat mech, the textbooks usually start by saying that you have some system. It's coupled to some reservoir with which you can exchange energy and particles. And so all ensembles, microcanonical, canonical, grand canonical, are all the same. Let's not do that. Let's ask a different question. Let's say I have some well-isolated quantum system, many degrees of freedom, all interacting together. So this is the sort of setup that you can very naturally get in synthetic quantum systems. Many interacting but well-isolated quantum degrees of freedom. And we'd like to understand the long-time behavior of the system. And of course, this is a many-particle quantum system. It's described by some wave function, call it psi, and the time evolution of this wave function psi is given by the Schrödinger equation with some Hamiltonian h. But what we'd like to know is to have a sort of good statistical understanding of what sort of long-time behavior this many-body quantum system exhibits. Yeah? Now, what might we expect? Well, our intuition is that systems should go to thermal equilibrium. Yeah? But now, in terms of like the most simple-minded intuition, there's a problem, which is that we think of the process of going to thermal equilibrium as being associated to a loss of memory of the initial conditions. So if I have some cup of coffee and I pour some milk into it, and I wait a while, it goes to equilibrium, it settles down to some uniform light brown color, and all I can tell is what's the temperature. Yeah, I don't know where exactly the milk was poured in. That information about the initial condition has been lost. Now, if we're doing quantum dynamics, then the Schrödinger time evolution is formally unitary, which means it preserves all information about the initial conditions to all times. So how do we square this with our intuition that things should thermalize? Well, that's a problem that we know how to solve. It turns out that, look, if the only way that you can access and reconstruct information about the initial condition is to measure every single one of an Avogadro's number of degrees of freedom, well, that's not actually accessible. Yeah? The measurements you can actually make on a system are few body measurements, typically spatially local observables. And so the meaningful question is, given the measurements we can actually make, which are few body, spatially local, and so forth, does a system look as though it's gone to thermal equilibrium or not? Yeah? If the information about the initial condition, if the only way to extract that is by measuring global observables, then that information for all practical purposes is inaccessible. Yeah? So this is the effective question that we really want to understand, the answer to understand if the problem goes to thermal equilibrium or not. Now, this is intimately, now let's go back to sort of undergrad stat mech. So when we learn undergrad stat mech, we learn about macrostates and microstates. So macrostates are characterized by these sorts of measurable physical properties of the system, whereas microstates contain detailed information about every degree of freedom, position, momentum, and so forth. Yeah? The lovely thing about stat mech is you don't actually need to know the details of the microstate. You only need to be able to make predictions about the macrostate. And of course, there's lots of microstates corresponding to each macrostate. Yeah? And a foundational idea in statistical physics, which dates back all the way to Boltzmann, is the idea of ergodicity, which says that essentially if you wait a long time, the system explores all of its microstates which are consistent with the conservation laws. Yeah? Conservation laws being things like charge conservation. So you can only access all the microstates which have the same total charge as the state you started in. So this is this idea of ergodicity, that the system explores all of the sort of configuration space allowed by conservation laws. This is absolutely fundamental to stat phys. Yeah, this is where books on statistical physics usually start. But what if Boltzmann was wrong? Yeah? What if you could have systems which did not obey ergodicity? Well, then you would be in here there be dragons territory, and you can throw out your textbooks and start from square one. And what this talk is going to be about is settings in which ergodicity is broken. Yeah? Where you don't have ergodicity, you have stuff that sort of goes beyond Boltzmann. So how could ergodicity be broken? Well, for the purposes of this talk, I'll be sticking to quantum dynamics. There's a sort of separate strand of research looking into ergodicity breaking in classical systems. I will not be talking about that. The earliest route to ergodicity breaking of a sort that was known in quantum dynamics is you could have integrable systems. So integrable systems are systems with infinitely many conservation laws, or extensively many conservation laws. So this requires a high degree of fine-tuning. And there's no argument for robustness of quantum integrability that I know of. So it's entirely possible that you have a quantum integrable system, you perturb it a little bit, and the ergodicity breaking goes away. Yeah? Which is to say that that ergodicity is restored on some time scale that will generically be just a low-order polynomial in the perturbation strength. So the time scale will just be set by Fermi's golden rule or something like that. Okay, more recently people have discussed quantum scars, which is also a case where you have ergodicity from generic initial conditions, but not from some very special initial conditions. But that, again, appears to be a fine-tuned phenomenon. You perturb the Hamiltonian a little bit, and the scars will go away on some time scale that's just set by Fermi's golden rule, or it's sort of low-order polynomial in the perturbation strength. So, OK, if you're willing to fine-tune things enough, you can violate ergodicity. But stuff that's very fine-tuned is not as interesting. So what I'd really like to have is robust routes to ergodicity breaking. And what I'll tell you about in this talk is 3 distinct routes to robust ergodicity breaking, which have been extensively explored over the past 20 years. And this is sort of presented in chronological order of when they were discovered, but also sort of like increasing order of robustness in a sense that should become clear as we proceed. So let's start with the first to be discovered. This is a phenomenon that is known as many-body localization. So this is something that happens in systems with strong quenched disorder. So you can think of this as strong inhomogeneity. And what happens there is essentially that excitations get trapped on disorder. So you can think of this disordered system as having a very inhomogeneous potential landscape. And you're looking at energy-conserving dynamics. So particles get trapped either in minima or even on maxima. Because if you're sitting on a maximum and you roll off the maximum, that reduces the energy. But the energy has got to go somewhere. This is energy-conserving dynamics, so you can't do that. So excitations can get trapped on disorder, breaking ergodicity. Now, for single particle systems, this has been known for a long time. Actually, this is the result for which Anderson won his Nobel Prize. In the last 20 years, there's been a growing appreciation that this can happen even for interacting many particle systems at non-zero energy density. And this is robust in the following sense. There exist special points. Well, OK, first of all, let me say, in order to get many-body localization, you need your system to be perfectly isolated. You cannot be coupled to any heat path. And you need energy conservation, at least of Floquet type, modulo some discrete amount. Without energy conservation, there's no such thing. If you have a well-isolated energy-conserving system, then it is robust in the following sense. There exist special points in the space of all Hamiltonians where this localization is exact, and you can prove that to infinite times, there's no ergodicity. And then when you perturb about those exactly solvable points, then maybe you do, the generic behavior is you do restore ergodicity, but the time scale on which you restore ergodicity is non-analytic. So as you take the strength of the perturbation to 0, the time scale diverges faster than any polynomial function of perturbation strength. Typically, it might diverge exponentially fast in perturbation strength. And this should be contrasted with, for instance, integrability, where the time scale was just Fermi's golden rule, so g squared or something like that. So it's robust in the sense that the time scales are very long. They're super polynomially long in perturbation strength. And for the special case of 1D spin chains, the time scale may actually be infinite for sufficiently weak perturbations, although this claim is still controversial. And of course, the spin chain model itself is not going to be valid to infinite timescales. So this is the sense in which many-body localization is robust. Now, why is it interesting? Well, one reason why it's interesting is this is sort of historically the first model of ergodicity breaking, which is robust in the sense that I just introduced. But another reason that it's interesting is that once you break ergodicity, at least out to these enormously long time scales, you can find new sorts of phenomena which have no analog in thermal equilibrium. And a good example of this is spontaneous symmetry breaking at non-zero energy density in one dimension. So let me illustrate sort of new physics that can result by talking about that. So let's start by now, again, going back to StatMech class and reviewing the notion of spontaneous symmetry breaking. So the idea behind spontaneous symmetry breaking is that the state of a thermodynamically large system may not respect all of the symmetries of the Hamiltonian. And the canonical example for illustrating spontaneous symmetry breaking is the transverse field Ising model. Yeah? So the Hilbert space here consists of spin 1/2 variables arranged on a line in one dimension. The Hamiltonian takes the following form, where the sigmas are Pauli matrices. Usually you just write down the first two terms, but if I have just the first two terms, this is an integrable model in disguise. So I add an extra term just to break integrability. The thing about this Hamiltonian is if you take every sigma z to minus sigma z while leaving sigma x unchanged, then the Hamiltonian is unchanged. Yeah? So this is a global Ising symmetry. But it's well known that the ground states of the transverse Ising model take the following form, plus some dressing by quantum fluctuations. And these ground states are not invariant under the global Ising spin flip. Yeah? So this is the sense in which the transverse field Ising model spontaneously breaks the symmetry. The Hamiltonian has a symmetry. The ground states do not. And you can diagnose the symmetry breaking in various ways. So one way is you could pick one of these ground states, either with the plus sign or the minus sign, and you could look at the equal time correlation functions of the spin. And you would see that these equal time correlation functions had long-range order in space. Something else you could do is you could prepare the system in an initial condition, which was a superposition state. Yeah, so let's say the all plus state, which is a superposition state of the true ground states with the plus sign and the minus sign. And that superposition state breaks the Ising symmetry. And then you could look at the subsequent dynamics and ask how long it takes the internal dynamics of the system to restore that symmetry. And the autocorrelation functions would have long-range order in the time domain out to times exponentially long in system size. Yeah? So you could either look at correlation functions in space or in time as a way to diagnose spontaneous symmetry breaking in the transverse field Ising model. You could also look at susceptibilities, but that's very much an equilibrium thing, so I don't want to talk about that diagnostic. Now, the ground state of the Ising model is well known to spontaneously break symmetry. The excited states of the Ising model do not spontaneously break symmetry. Yeah? And there's theorems about this in the StatMech textbooks. So for instance, the Landau-Peierls theorem, which says that there is no spontaneous symmetry breaking in one space dimension at non-zero temperature. And we can even understand this microscopically. So you could have domain walls, which are places where the spin pattern changes from up to down. Domain walls have entropy, which is logarithmic in system size. They have energy cost, which is constant. So at any non-zero temperature, the entropy of the domain walls dominates over the energy. You introduce domain walls into the problem. The domain walls can run around. When the domain walls run around, they allow these correlation functions in both space and time to relax. Yeah? So you lose the long-range order, which was your diagnostic of spontaneous symmetry breaking. OK, so that's what the textbooks tell us. Now, let's move to new physics. Same Hamiltonian as before, except these coefficients I will now choose from some distribution. So I will choose these coefficients to be random. If the distribution from which they are drawn is sufficiently broad, then the excited states also have the structure of some particular spin pattern plus or minus its all spin split counterpart, plus some dressing by quantum fluctuations. And the key thing is now, if I have domain wall sitting on this side, if that domain wall hops right or left, that changes the energy, because each of these bonds has a different strength. And if this randomness is very strong, and I have energy conservation, then these domain walls cannot freely run around. So the domain walls are trapped on specific sites. Yeah? And the upshot of that is that my correlation functions now once again have long-range order. My autocorrelation functions have long-range order in the time domain. So if I prepare some initial condition, which is that non-zero energy density, like spins up here, down here, up here, down here, some non-zero density of domain walls in the initial condition. This is an initial condition which breaks the Ising symmetry. But now if I look at autocorrelation functions in the time domain, I'll have long-range order because the domain walls cannot move around and relax the long-range order. We'll also have long-range order in the space domain, although this will be of spin glass type, it'll either plus sign or minus sign, depending on how many domain walls you've crossed. So you have spontaneous symmetry breaking in one dimension at non-zero energy density, which is something that was supposedly forbidden by the Landau-Peierls theorem from the textbooks. But the Landau-Peierls theorem assumed ergodicity, We don't have ergodicity, so the textbook theorems don't apply. Yeah? And so you can have new sorts of phenomena, such as spontaneous symmetry breaking at non-zero energy density in one dimension, which the textbook said you couldn't have. Yeah? So this is the simplest and first example of new physics of this kind. There are others. The most famous is probably time crystals, which I will not talk about, but you may have heard about. And the bottom line is that, look, you can get new physics once you break ergodicity. Yeah? And this was one way of breaking ergodicity. Now, is many-body localization the only game in town for ergodicity breaking? Well, 5 years ago, I'd have said it's the only one that we know about. Yeah? But time passes, and now there's others. So the rest of the talk will be telling you about other routes we discovered to the breaking of ergodicity. Yeah? So now this brings me to part 2 of my talk, which is ergodicity breaking from what I will call fractonic symmetries. Yeah? So what are fractonic? Well, so this is an alternative route to ergodicity breaking. It was inspired by the study of fracton phases of matter. Now, you don't actually need to know anything about fracton phases of matter for this talk. If you were wondering what they are, they're a sort of generalized quantum spin liquid in which the elementary excitations have fractionalized mobility. So elementary excitations are immobile, but if you look at composites of multiple elementary excitations, they can be mobile. You don't actually need to know any details. What you do need to know for the purposes of this talk is that this new route to ergodicity breaking, unlike many-body localization, will not require energy conservation. So it will be robust to noise. You can break time translation invariance, no problem. It also will not require disorder, so you can get it in translation invariant systems. Instead, what we will require is a finite number of conservation laws. Yeah? And 2 is sufficient. You have to pick the right 2, and a sufficient set of 2 conservation laws is charge conservation and dipole moment conservation. Dipole moment defined in the obvious Maxwell E&M sense. And it turns out that the interplay of these 2 conservation laws is sufficient to break ergodicity. And will also require sort of strict locality in real space. OK, so everything should be made as simple as possible and no simpler. So the simplest setting in which the story plays out is you can go down to 1 dimension on a lattice, let's say a 1D spin chain. Yeah? And we'll consider a 1D spin chain where the z component of spin is conserved. I'll call that charge. And also the dipole moment is conserved, which is defined in the obvious way as the position-weighted z component of spin. Yeah? And for specificity, let's say it's a spin 1 chain. So each side can be spin up, spin 0, or spin down. But you could make it spin whatever, spin s if you wanted. OK, now what we want is that charge is conserved and dipole moment is conserved. Yeah? So we're going to be looking at dynamics, which is locally generated in real space. So it's generated by sort of local operators. And it conserves these 2 quantities. It conserves charge. It conserves dipole moment. No other structure. What this immediately tells us is that an individual charge is immobile. Because if an individual charge moves, that changes the dipole moment. But if you have a plus charge and a minus charge next to each other, that can move freely. Yeah? Or if you have 2 positive charges, they can exhibit cooperative motion in a way that preserves the dipole moment, or if you wish, the center of mass. Yeah? OK. Yeah. And so you can have this sort of process, which you could interpret either as charge hops to the right and emits a plus-minus dipole to the left, or as charge hops left and emits a plus-minus dipole to the right. So we want to consider quantum dynamics, which is locally generated, and which has these 2 conservation laws. So the simplest way to implement that is in what's called a quantum circuit model. So what's a quantum circuit model? Well, you have some wave function. The wave function undergoes evolution. Time evolution is generated by building up a circuit out of a bunch of local unitary gates. If you're not used to thinking about circuit model time evolution, you should instead think of you have Hamiltonian time evolution, e to the iht, and then you do a Suzuki-Trotter decomposition of Hamiltonian time evolution into little time slices, and what you get is this sort of time evolution that's generated by a bunch of local unitaries. And each of these unitaries should conserve charge and dipole moment, but we impose no other structure. Yeah? So in particular, you could choose these unitaries uniformly in space or randomly in space. It doesn't matter for the answers. Yeah? So you could have disorder or not have disorder, you get the same results. You could choose them uniformly in time, which would mean you had energy conservation, or you could choose them randomly in time, meaning noisy dynamics, no energy conservation. Again, same answers either way. Yeah? So that's the simplest way in which you can set this up as, you have two conservation laws and spatial locality, and that's it. No additional structure. Now, what would we expect? Well, this is sort of minimally structured dynamics, so I think our default expectation should be ergodicity. Yeah? And what would ergodicity mean? Well, you start the system off with a certain value of charge and dipole moment. Those are conserved quantities. They can never change under the dynamics. But then you might think that the system would explore all of its configuration space with the same quantum numbers of charge and dipole moment. Yeah? So you might think the long time average of the charge distribution would be sort of equipartition over all states with the same charge and dipole moment. Yeah? And if you construct a sort of equipartition, then you conclude that charge should be essentially uniformly distributed over the system. And that's sensible. That's what we expect. You start with some system, charge spreads out uniformly over the system. Yeah? But now you start the system off with charge sitting on a particular site, let's say number 4. You run the time dynamics, and you see something very different. Charge spreads out a little bit, but even in the long time limit, it very much does not approach equipartition. What you get looks very different from what equipartition would have predicted. So, surprise, yeah? What's going on? Well, that's something, bottom line result is for this minimal implementation that I gave you, it looks like charge is localized. Yeah? And charge is localized starting from almost any initial condition. Now, if I increase the range of the operators which I was allowing, then typical initial conditions would appear to obey equipartition, but there would still be an exponentially large number of initial conditions which did not, and which apparently violated equipartition and ergodicity and displayed behavior that looked like localization. Now, this cannot be conventional sort of Anderson or many-body type localization because there's no energy conservation. I could make my dynamics random in time. And also, there's no disorder. I could make my dynamics uniform in space. Yeah? So it's something new. What is it? Well, we figured it out a few years ago, so this I'll tell you about. So it's easiest to illustrate this constructively. Yeah? So let plus be the state of locally maximal positive charge, and let minus be the state with locally maximal negative charge. And let's consider a state which alternates between all plus and all minus regions. So obviously, key here is the domain walls where the pattern changes. And these domain walls are assumed to be at least as far apart as the biggest operator that generates my dynamics. Now let's come in and look at the dynamics of the state. Every operator acts across either 0 or 1 domain walls by construction, never across 2 because the domain walls are too far apart. If it acts across 0 domain walls, it acts on a state that's locally extremal charge. Nothing you can do to that consistent with charge conservation. If it acts across 1 domain wall, you might think you could reshuffle plus and minus charges, but that would change the dipole moment. Yeah? If you're acting across only 1 domain wall, you're acting on a state that's locally extremal dipole moment. So there's nothing you can do to that consistent with dipole conservation. Yeah? So any state of this sort must be an exact eigenstate of any quantum dynamics that conserves 2 charges, charge and dipole, and is locally generated on the scale m. Now, how many states like this are there? It's easy to establish a lower bound. You can carve up your system into blocks of size little m. Each such block can be freely allowed to be either all plus or all minus. Yeah? And that gives you at least this many states, which are exact eigenstates of any dynamics with these 2 conservation laws plus locality. Meanwhile, the number of symmetry sectors is only polynomially large in system size. Yeah? So these different states, which are exact eigenstates, they're not living in different symmetry sectors. That's not what's going on. Yeah? You've only got polynomially many symmetry sectors, but you've got exponentially many of these simple product states which have no dynamics. Yeah? So manifestly, ergodicity is broken. And I should say that this generalizes to any number of dimensions d. Yeah? So the argument proceeds essentially by induction. If you're in d dimensions and you conserve charge and also all d components of dipole moment, then you have exponential in system volume number of these exact eigenstates, which are exact eigenstates of any dynamics which conserves charge and dipole and is locally generated in d dimensions. Yeah? Let's drill into the time dynamics a little bit more. So time evolution in quantum mechanics is generated by a unitary matrix. And that unitary matrix is always block diagonal by symmetry sector. And what that means is that quantum dynamics does not change the symmetry quantum numbers. Yeah? If you start with one set of symmetry quantum numbers, you always have the same set of symmetry quantum numbers. And in an ergodic system, that's it. The unitary time evolution matrix is block diagonal by symmetry sector, but then within each symmetry block, it's just a random matrix. That's not what we have here. What we have here is something very different. You have this unitary matrix. It's block diagonal by symmetry sector. But then within each symmetry sector, you have a further block diagonal structure where you get exponentially many subblocks, some very small, these 1 by 1s, some of larger size, some with size that diverges in the thermodynamic limit. So these subblocks are called Krylov subsectors. And the dynamics never takes you from one Krylov subsector to a different Krylov subsector, even if both of those have the same symmetry quantum numbers. So we're breaking ergodicity. We're sort of exponentially breaking ergodicity. You don't explore all of the symmetry sector. You don't explore all of the allowed configuration space. You only explore those other points in configuration space which are in the same Krylov subsector. Yeah? So this is called shattering or fragmentation of Hilbert space. And it's robust to any perturbation that respects these two conservation laws and is locally generated in real space. Now, charge and dipole moment may seem like a very artificial set of conservation laws to impose. Actually, there's a very simple way to get them. So the simple way to get them is you take ultra-cold atoms in an optical lattice and you tilt the lattice. Yeah? So atom number is conserved. Atom number is analogous to charge. The quantity analogous to dipole moment is center of mass. Yeah? If this optical lattice is tilted, then the tilt couples to center of mass. If the tilt is strong and energy is conserved, then center of mass cannot change without changing the energy. Yeah? So you get atom number conservation and center of mass conservation analogous to charge and dipole moment conservation. And with this sort of implementation, in fact, this sort of ergodicity breaking has already been seen by multiple groups. Okay. What have we accomplished? Well, we found an alternative route to ergodicity breaking, which does not rely on energy conservation or on disorder. Instead, it relies on two symmetries and locality. Now, time for a little aside. I said ergodicity is broken. I said that there was this big distribution of some small subblocks within each symmetry sector, some big subblocks. So far, I was focusing on the small subsectors, especially the sectors of size 1, yeah, which were these states that had no dynamics. But there are also large subsectors with size that diverges in the thermodynamic limit. If you start in those large subsectors, what you get looks like equipartition with respect to all states in that subsector, and there's a diverging number of those. So it looks like you get thermalization of a sort. Yeah? And now you could ask about the approach to thermal equilibrium, where now thermal equilibrium is defined not with respect to the entire symmetry sector, but just with respect to this diverging size subsector. Yeah? So now what would we expect? Well, we got quantum dynamics with conservation laws. So default expectation should be that we would have hydrodynamics. Usual long-time behavior would be diffusion. So right up here is the diffusion equation. The diffusion equation has this characteristic relationship where length scales go like square root of time. Yeah? Now, in this setting, that's not what we get. So the approach to equilibrium is still given by hydrodynamics. But it's not diffusion. Instead, it's subdiffusion. Yeah? And there's a huge number of subdiffusive universality classes that can be accessed in this way. And this structure is pretty robust. So there's a simple way to see that it cannot be just diffusion. Yeah? And that's to say that, look, charges are not mobile. The mobile objects are dipoles. Now, dipoles feel no force in uniform field. So if you apply a uniform field, nothing should happen. Yeah? So the conductivity of the system should be 0. And there's the Einstein relation, which says that diffusion constant is proportional to conductivity. So if conductivity is 0, then the diffusion constant is 0. And so the approach to thermal equilibrium better be slower than diffusion. And we can figure out what it is. Start with some continuity equation. So there's a charge density. It depends on currents. But the current is now a 2-index object because you have dipoles in direction I moving in direction j. And then to balance indices, you need 2 derivatives here. So you get a continuity equation that looks something like this. You could derive this formally if you wished. But you can sort of guess that it should look something like that. And then that's not sufficient. You also need the analog of Fick's law, which tells you how currents are determined by density gradients. So again, the mobile objects are dipoles. Dipoles move in response to gradients in the electric field, which means they move in response to 2 derivatives of the density. Put that back. So you get a Fick's law, which has 2 derivatives in it instead of 1. The continuity equation also had 2 derivatives in it instead of 1. Put it all together, and you get a generalized diffusion equation that looks like this. Yeah? So here, n is the number of multipole moments. If n is 0, that's you conserve monopole charge only. That's the ordinary diffusion equation. Yeah? If n is 1, that's charge and dipole conservation. You have 2 extra derivatives, one from the continuity equation, one from Fick's law. If n is 2, that's charge, dipole, and quadrupole. That's now you have 4 extra derivatives. Yeah? And so you can access, in principle, an infinite family of subdiffusion equations by sort of adding additional multipole moment conservation laws. And now you do a dimensional analysis, and you'll conclude that length scales go like time scale to a smaller power. So this is subdiffusion, and each time you add an extra conserved multipole moment, the subdiffusion gets slower. So there's an infinite family of subdiffusive hydrodynamic universality classes that we can access in this way. Again, you can realize this most straightforwardly with cold atoms in a tilted optical lattice. And in fact, this has already been observed by Wasim Bakr's group, where they saw this sort of t to the 1/4 subdiffusion with charge and dipole conservation. OK, little bit of an aside over. Yeah? Now let's get back to the sort of main menu, which is talking about ergodicity breaking. So we've seen 2 ways to break ergodicity. First, we talked about many-body localization, which needed energy conservation. But given energy conservation and strong disorder, it was robust to local perturbations. Yeah? Then we saw this Hilbert space shattering or Hilbert space fragmentation phenomenon from these sort of unusual symmetries, which did not need energy conservation and did not need strong disorder, but instead it needed these 2 somewhat unusual conservation laws, and it needed spatial locality. Can we do better? Can we get ergodicity breaking, which is robust to arbitrary perturbations without symmetry restricting the perturbations and without even demanding spatial locality? Yeah? So this seems like a very big ask. Certainly nothing that we knew about more than 2 years ago was capable of doing this. But now it turns out actually, yes, there is a way to do this. And we figured out how to break ergodicity in a manner that's robust to arbitrary perturbations. And that's what the last part of my talk will be about. Yeah? So again, so the key thing here will be these higher form symmetries. So what are higher form symmetries? Well, in the undergrad curriculum, we talk about global symmetries. So global symmetries, the symmetry operator acts everywhere in space. Yeah? So the Ising symmetry that we talked about earlier is an example of a global symmetry. And we also talk about gauge symmetries, where the symmetry operator acts on points. Yeah? Higher form symmetries are intermediate between global symmetries and gauge symmetries. So the symmetry operator acts on a manifold, but it acts on a deformable manifold. with dimension bigger than 0 and less than the dimension of space. And it turns out that sort of these emergent higher form symmetries are precisely what we need to give rise to this sort of super strong ergodicity breaking that I was referring to. All that we're going to require for this last part of my talk is enforcement of a single constraint. You have to allow me some structure, and this is the minimal amount of structure that I could demand. One constraint, that's it. Allow me one constraint, and I can break ergodicity in this super strong manner. Okay, again, it's nicest to illustrate things with explicit examples. And the simplest explicit example that does this is what we call the CZP model. So what's the CZP model? Well, the Hilbert space is spin 1/2 variables which are arranged on a square lattice in 2 dimensions. Yeah? So this is square lattice, and I have a spin 1/2 on every vertex. And I'll have a Hamiltonian, and the Hamiltonian will have the form H0 plus V. V is my perturbation. V can be anything, or anything k local. So it could be sum over xi. It could be sum over xi xj. It could also be sum over xi yj zk, where I, j, and k are freely summed over. Yeah? So here x, y, and z are Pauli spin operators, and the I, j, and k could be chosen freely anywhere in space. There's no requirement that they be spatially close to each other. Yeah? The only requirement is that this perturbation V, should be k local, which means it can be written as a sum of terms where each term in the sum acts on no more than k degrees of freedom, where k is bounded. K could be 5 million. That would also be fine. So this is a very weak constraint to place on V. It's a non-global perturbation. Yeah? And for any V, I claim that this model is going to break ergodicity. So obviously, H0 has to be somewhat special. So now let's talk about what H0 is. So H0 has the following form. H0 is sum over all plaquettes. So this is a sort of elementary plaquette of the square lattice. And on each plaquette, you act with this operator CZP. So for the quantum information, sort of familiar people in the audience, you can define CZP as a product of controlled Z gates on the 4 bonds of each elementary plaquette. For people that don't speak quantum computation, instead, you can write CZP in terms of Pauli Z operators in the following way. Yeah? So you have ZZ interactions on the diagonal, and you have a 4Z interaction around the spins of an elementary plaquette. And what this does is it penalizes having an odd number of upspins adjacent to each other on any elementary plaquette. So on any elementary plaquette, you can have 0 adjacent upspins, or 2 adjacent pairs of upspins, or 4 adjacent pairs of upspins, but you can't have just 1. OK. That's what this does. Anytime you violate this constraint, anytime you have an odd number of neighboring upspins, then you pay some large energy penalty of order j. Now, if we say that we want to always satisfy this constraint, so we project into some subspace which always satisfies this constraint, how big is that subspace? Well, that subspace is this big. What I want you to take away from this is that this subspace is exponentially large in system volume, which means it's big enough to accommodate a non-zero entropy density. And so we can sensibly talk about thermalization or lack thereof within this constrained subspace. Now, in order to understand things at a more detailed level, it's useful to introduce a duality. So if I have this Hamiltonian actually has 2 Ising symmetries. So it's defined on the square lattice, which is bipartite. There's an odd sublattice and an even sublattice. And if I do the global Ising spin flip, so I flip every spin on the odd sublattice, that's a symmetry. If I flip every spin on the even sublattice, that's a symmetry. So motivated by that, let's introduce a domain wall picture where I have 2 species of domain walls. I'll color them red and blue, and these correspond to the domain wall of the two Ising symmetries. Yeah? And in this dual representation, my constraint that I cannot have an odd number of neighboring upspins on any plaquette is equivalent to saying that the two colors of domain walls, red and blue, cannot intersect. Yeah? So my low energy Hilbert space is a Hilbert space of two species of domain walls, red and blue. Being domain walls, they have to form closed loops. Yeah? So it's two species of closed loops, red and blue, and the loops of different colors cannot intersect, but they can fluctuate freely, subject to the constraint that loops of different colors cannot intersect. Yeah? OK, now let's consider a configuration of the following sort. So this is meant to be a dense packing of system spanning loops, which alternates red, blue, red, blue, red, blue, red, blue. Yeah? There's a huge number of configurations like this because the loops can wiggle any which way. Essentially, every row you can either go to the right or to the left. So there's exponentially many configurations of this kind. But once you have made a configuration of this kind, then any local fluctuation is going to lead to constraint violations. It'll lead to an intersection of two loops. And moreover, this won't just be a virtual state. Yeah? It's not that you can sort of temporarily fluctuate into a virtual state which violates this constraint and then come out of it. The only way to change this pattern is to either delete an entire loop or to put a kink in this entire pattern. But either of those things involves acting on order L spins, where L is system size. Yeah? And I only have k local perturbations at my disposal. So I cannot do this at any finite order in perturbation theory. Yeah? Which means that, well, OK, if the constraint is imposed as a hard, exact constraint, then these are exact eigenstates to infinite time. If the constraint is imposed softly, meaning I'm allowed to violate it, but constraint violations cost some large amount of energy, then I can lean on the existing rigorous theory of pre-thermalization to establish a bound which says that these states live for a time that is exponentially long in the perturbation strength. Yeah? And remember, what I wanted is that my timescale for restoring ergodicity should be super polynomially long, and exponentials are definitely super polynomial. Yeah? So I have ergodicity breaking with these exponentially numerous states. Now, the aficionados in the audience may say, well, hang on, are you sure that you've resolved by all of your symmetries? Yeah? And that would be a very good question, because this system has an emergent one-form symmetry. So one-form symmetry in this context means that the symmetry operators live on arbitrary one-dimensional manifolds, and the symmetry charges are also loops. Yeah, they're sort of extended 1D objects. So we might think that the dynamics of some one-form symmetry would be like magnetohydrodynamics, dynamics of flux lines. And really, we should be resolving by the symmetry sectors of this one-form symmetry. So if we do that, what we find is that the unitary time evolution matrix block diagonalizes into symmetry sectors labeled by quantum numbers of this higher form symmetry. And there's two sorts of symmetry sectors. So there's one sort of symmetry sector in which the dynamics is ergodic after you properly resolve by symmetry sector. Yeah? And it obeys essentially magnetohydrodynamics. It's the hydrodynamics of flux lines. And there's another sort of symmetry sector which is made up entirely of these densely packed configurations in which there's no dynamics whatsoever. Yeah? So this model has ergodicity breaking, and it's ergodicity breaking which is robust to arbitrary perturbations, but the ergodicity breaking is sort of all or nothing in nature. Once you resolve by the emergent symmetries, there's some symmetry sectors that are ergodic. There's other symmetry sectors where there's no dynamics whatsoever. This all or nothing nature is an artifact of this particular model. You can get to something much more robust if you generalize the model. A simplest way to generalize the model is to go from spin 1/2 variables to clock spins. Let's say you have m state clock spins. If m is equal to 2, then this gives back the model that we just had. If m is bigger than 2, then you get new physics. Yeah? And let's say m is 3. So 3 is bigger than 2. So if m is 3, then instead of having 2 species of domain walls, you have 3 species of domain walls. Let's call them red, blue, green. The low energy Hilbert space now consists of 3 species of loops, red, blue, green, with the analogous constraint that loops of different colors cannot intersect, but they can fluctuate any which way, subject to the constraint that loops of different colors do not intersect. The constraint satisfying Hilbert space is still exponentially large in system volume. And now let's consider a state of the following form. So this contains some non-contractible loops and also some contractible loops. Yeah, this is a sort of generic state. And now what I'll do is let's start at the left and let's walk from left to right. And every time we encounter a system spanning non-contractible loop, we will record the color of the non-contractible loop. So in this case, that record would be green, red. Yeah? So what we would get is a label. Yeah? It's a label which records a sort of ordered sequence of non-contractible loops encountered as we walked from left to right. OK, that quantity is a topological invariant. There is no way to change it without sort of pushing this green loop through this red loop, which you cannot do for reasons similar to what I gave before. Yeah? So this label, this word, is a topological invariant. How many such words are there? Well, there's exponentially many in system size. Yeah? It's the set of all words written in m letters with length at most L. So there's exponentially many words that I could write down, and there's only polynomially many symmetry sectors. And moreover, now I can write down words which are symmetry neutral, but non-trivial. So something like red, blue, green is a word which has no symmetry charge associated to it, but it's a non-trivial word. Yeah? So now, ergodicity breaking is not all or nothing anymore. OK, there's still the densely packed sectors which have no dynamics. But now, in fact, in generic symmetry sectors, you get a further block diagonalization, where the unitary matrix within a generic symmetry sector block diagonalizes into distinct sub-blocks, where each sub-block is labeled by this invariant word, which is a topological invariant of the dynamics. And the dynamics never mixes states labeled by different words, even if those states have the same symmetry quantum numbers. Yeah? So now it's no longer all or nothing in character. It's super robust, same as in the CZP model, works in higher dimensions. I guess if you go to 3 dimensions, you want to consider membranes instead of loops. But the bottom line is now this gives extremely strong and extremely generic ergodicity breaking. Yeah? OK, so that brings me to my conclusions. Textbook statistical mechanics begins with Boltzmann's ergodic hypothesis, which says that the system explores all of its configuration space consistent with conservation laws. We'd like to understand how we can robustly break ergodicity in many-body quantum dynamics. I talked about 3 ways to do this. The first was many-body localization, which needs energy conservation and strong disorder, and then is robust to local perturbations. Then we talked about fractonic symmetries, which requires at least 2 symmetries, and which requires at least 2 symmetries and spatial locality, but does not require either energy conservation or disorder. And finally, I talked about this new route to ergodicity breaking based on higher form symmetries, which requires enforcement of a single constraint. That's it. And then it's robust to arbitrary k-local perturbations. Yeah. OK. Can we do better still? Well, that's something we're actively working on. But that's all I wanted to say for today.
Well done, Professor. We'll take some questions here. Yes?
So maybe more of a basic question, but I'm just curious if a system is ergodic, then when you say that it will visit all of the microstates, are you sort of casting aside like the probability of each microstate, like if the system's not in thermodynamic equilibrium? Like if
Well, OK, so standard Boltzmann theory. So the question was, what about the probability of each microstate? Yeah. So standard Boltzmann theory would say that every microstate is equiprobable, and you just cycle through all of them. Yeah. In this case, or in these settings, that's not the case. Now you start, some subset of microstates is equiprobable. That's all the microstates in that Krylov sector, and all of the other microstates have probability 0 of ever being sampled. Oliver?
The fractonic symmetries and the higher form symmetries seem to both of the symmetry structures involve higher dimensional objects in some sense. Is there a unified treatment that you can give that sort of brings both of these under a single umbrella for understanding them?
Well, I mean, the fractonic symmetries didn't have to be higher dimensional, right? So I gave you a one-dimensional example, 1D spin chain with charge and dipole.
But higher dimensional in the sense that, like, the dipole current was a 2-index object.
Okay.
That's the sort of thing you also get with higher forms.
Right. Yeah, so that structure is present, yeah, in both of them. I don't know if there's a simple unification of those two things. So there, the standard lore would be that the gauge theories describing fractons are symmetric tensor gauge theories, whereas higher form theories would be antisymmetric tensor theories. So okay, I suppose tensors, either symmetric or antisymmetric, but other than that, I don't know if there's a crisper connection.
For a long time, when we talked about symmetries, we only thought about currents with one index entirely. So the fact that it's generalized in both of these ways, and both of those generalizations end up having this ergodicity breaking, is just a striking pattern.
Sure. Yeah. Of course, when you have the ergodicity, like the strong version of the ergodicity breaking, it doesn't really make sense to talk about currents, right? The sort of current and hydrodynamic sort of description only makes sense when the ergodicity breaking is relatively weak, or you're starting off in some subsector which is thermodynamically large. If you started in one of these exact eigenstates, what current? There's no dynamics whatsoever. But yes, it is characteristic of these ergodicity breaking systems that if you pick an initial condition where you have something that looks like thermalization, which will not be every initial condition, just some of them, then yeah, you have descriptions which involve sort of currents with more indices.
I think we have time for one or two more questions.
Yeah, so in these settings, can you compute or even define any interesting macroscopic quantities like in textbook StatMech?
The question is, can you define macroscopic quantities? Well, I mean, you can define observables, which could be macroscopic. So you could talk about correlation functions or magnetizations or something like that. So you can certainly talk about sensible macroscopic observables. It's just that those observables will be exquisitely sensitive to the initial condition, right? Which is not what you have in normal StatMech. So in normal StatMech, you change the initial condition a little bit, and the time dynamics of observables only changes a little bit. Now here you change the initial condition a little bit, and the time dynamics of the observables could change completely.
Does it reach an equilibrium?
Well, okay, so the question is, does it reach equilibrium? I mean, it depends. So if you started in one of these exact eigenstates, it has no dynamics whatsoever, so it stays in its initial condition forever. If you started in a different initial condition, maybe it has some dynamics, and it reaches a state that looks like equilibrium, but it's not true equilibrium, meaning equipartition over the entire symmetry sector, but it's just equipartition over some subset of the symmetry sector.
Sounds non-ergodicic.
Yes.
Thanks. Does this mean we have to be a little bit careful about our use of concepts like temperature and entropy and
yes.
in classical applications?
Yes, neither temperature nor entropy really makes sense to talk about if ergodicity is broken. Instead, you should just be talking about energy density, let's say.
Yeah, interesting.
And yet, at least so far, these are specialized systems.
Yes, I mean, at least minimally specialized. Yeah.
All right, last question here, I think. And
So when to achieve classical StatMech, you need ergodicity and sort of mixing property.
Sure.
Is there analog in quantum where you don't have mixing but you have ergodicity?
Yeah, so if you could have something intermediate in quantum mechanics. I'm not aware of an example, but it would be interesting if something like this existed.
all right, you left something for next time. So please join me once again in thanking Professor Nandkishore. Who I'm sure will be pleased to take additional questions if you have them.